Okay, so welcome to sheet 8, which is all about motion and constant acceleration in one dimension, i.e. it's the Suvat equations. So these are in fact given to you in your formula book, and we're going to be working with these first 5 equations on the left. The vector equations we can use in 3D, and because we don't have a concept of squaring for a vector, there is only 4 when you're working in vector form. But in 1D, we've got 5. And the first example was to derive these equations. Well, we can do them in sequence. So I've got a velocity time graph. So for a velocity time graph, we know that the gradient is equal to the acceleration. So A, which was used for acceleration, is v minus u over t. And that implies that v is equal to u plus at, which is our third equation. So we've got these two. Equations 1 and 2 come from using the fact that the area under the curve is displacement. So area under the graph is displacement. And we're going to do this in a couple of ways. So the first thing I'm going to do is I'm going to split this into a rectangle and a triangle, equation 2 and equation 1. So S then is the area of 1 plus the area of 2. Well, that is just area of 1 is ut. Area of 2 is a triangle and it's half. The height is v minus u. The base is t. But v minus u from equation 3 can be rearranged to be at. So this essentially says that S is ut plus a half at times by t, which is our familiar S equals ut plus a half at squared. And that is equation 1. Still looking at the area, if I think about it as the big rectangle, take away this area. So S is the area of the big rectangle, take away the area of 1. When we have VT minus a half times t times v minus u, which is Vt minus a half at squared, which was equation 2. We can also use area to derive 4. So you can also have S being the area of the trapezium. So the area of the trapezium is the length of the two parallel sides. Well, I've got one side of u, length u, and one side of length v. But over 2, so it's the average of those times by the height of the trapezium, which is t. So that's equation 4. Well, I could just write that as u plus v times t. So that's equation 4. So we've only got one left to define, and that is 5, which is v squared equals u squared plus 2as. So for this one, using equation 3, we can find that t is v minus u over a. And I'm now going to substitute that into equation 4. Substitute into equation 4. So s is a half u plus v times by t, but we're going to write t as v minus u over a. That implies that 2as is u plus v, v minus u. So this is a difference of two squares, and we get v squared minus u squared, which I can rearrange to be v squared is u squared plus 2as, and that's equation 5. You need to know these derivations of these 5 equations. You should be able to do this from the graph. Okay, let's look at example 2, and this is about a fireworks. This is an application of the Suvat equation. So for part A, part A tells us some information. So starts from rest. So if something starts from rest, its initial speed u is 0 meters per second. Moves under the power of its motor, which burns for 5 seconds. So t is 5. And we're told it reaches a height of 42 meters at when the engine burns out, so after 5 seconds, so s is 42. So I can just go through here. I've got s, I've got u, I've got t. I want to find a. Well, I can use s equals ut plus a half at squared. So 42, u is 0, so that's 0, plus 1 over 2 times a times 5 squared. So a then is 84 over 25 meters per second squared. Part B is similar. So S, U, V, A, T. So again, S was 42, U was 0, T was 5, and I want to find V. So V then, so using V equals U plus A T, because I've just found A, I know that A is 84 over 5. Over 25, sorry, I think, yeah, 84 over 25. So V then is 0 plus 84 over 25 times by 5, which is 84 over 5 meters per second. So again, we've used a couple of our Suvat equations here. Of course, I could use other equations, because sometimes it can be dangerous to use this 84. This A equals 84 over 25 can be dangerous. So I could potentially use the S equals U plus V over 2 times by T to say that 84 over 5 is U plus V, but U is 0, so V equals 84 over 5. So that's the other way I could do example 2. Quite often I recommend that where possible, you don't use values that you have calculated, and you try and use the values that are given in the question, because it just saves in case you've made any mistakes anywhere. Now part C becomes a little bit harder, and I think it helps to think about what happens here. So imagine you've got the ground. In the first 5 seconds, it reaches this point here, and this point here is 42 meters high. It's moving now at speed, and we know that the speed at this point is 84/5, and the motor then burns out, so there's no acceleration upwards anymore. Assuming upwards is positive, then actually the acceleration is the force of gravity acting down. So this particle essentially moves up for a bit, reaches a highest point, and then comes back down and hits the ground. And it does all of that in under the motion of gravity. So if I set up my Suvat equations, I want to know how long it takes till it hits the ground. Well, it starts 42 meters up, so the displacement is minus 42, assuming upwards is positive. U is the 84/5 that I found in part B. V, I don't know. A is minus 9.8, and T is what I'm trying to find out. So I'm going to use using S equals UT plus a half AT squared. So minus 42 is equal to 84/5T minus 4.9 T squared. Well, I can rearrange this to say that 4.9 T squared minus 84/5T minus 42 equals 0. And this is just a quadratic that I can solve on the calculator. So T is equal to either 12 plus 2√561 over 35, or T is equal to 12 minus 2√561 over 35. Well, this one is negative, so not a solution. You can't have negative time. This one, though, is approximately 1.696 seconds. So the time since the launch is that plus 5. So about 6.7 seconds the rocket is in the air. Okay, so there's only 4 questions on this sheet, plus the exam questions that I'll attach. Please have a go at them and let me know if there's any questions.